I welcome you all in the online refresher course in chemistry hosted by Department of Chemistry, Gujarat University, Ahmedabad. On behalf of Dr. Jagdish Joshi, Professor Director UGC HRDC, and Dr. Dilip Wasawa, Assistant Professor Refresher Course Coordinator, Department of Chemistry, Gujarat University.
The next session is of Professor Dr. Pradeep Deota, former Vice Dean, Faculty of Technology and Engineering, former Head, Applied Chemistry Department, MS University of Baroda. Mr. Pradeep Deota has more than 29 years of teaching and research experience. He has filed 3 Indian patents and published over 45 research papers in various national international journals. He received Postdoctoral Science and Technology Agency Fellowship STA, Government of Japan, at Nation Institute of Material and Chemical Research, Tsukuba, Japan in 1997, accompanied as group leader mentor and trained the Indian students team to participate in International Chemistry Olympiad held in Japan 2010 with 3 silver and 1 bronze medal, and in Turkey 2011 with 2 gold medal and 2 silver medals. He has worked as postdoctoral research associate CSIR at IIT Mumbai in 1990. As a head, Applied Chemistry Department received grant of Rs 5 crore from Government of Gujarat to set up Center of Excellence in Polymers at Faculty of Technology and Engineering. Also worked as resource person at Homi Bhabha Center for Science Education TIFR Mumbai. Moreover, he has delivered number of academic talks at several places in India and abroad. He is an expert committee member of All India Council of Technical Education AICTE New Delhi. Also, he is a member of many academic bodies, selection committees of various school, colleges and universities. He was given a Best Teacher Award by Lions Club, Vadodara in 2011. Thank you.
Hello everyone, I am Professor Pradeep Deota. We will discuss today background and concepts of designing organic synthesis. As we all know, organic chemistry earlier was based on functional groups and it required great deal of memorization because it involved large body of facts. Today it is quite different and changing continuously. It is learnt and taught in terms of new theories of chemical bonding, such as molecular orbital theory, principle of conservation of orbital symmetry, functional group equivalence, methods of GC bond formation, and so on. This has minimized the need to memorize organic chemistry. And towards this change, a major role is played by organic synthesis. Organic synthesis has changed, has enriched our knowledge, it has discovered unsought facts, and it has provided deeper understanding of chemical reactions. Organic term was first used by Berzelius to distinguish them from inorganic compounds, and organic and inorganic compounds were distinguished by him based on the origin of those substances. The substances which are obtained from organs of plants and animals were called organic, and substances obtained from minerals and rocks were called inorganic. The organic chemistry was earlier used to be only study of compounds and their degradation studies and so on from natural sources. In those days, there was another very important theory which was going on, that is called vital force theory. This was also postulated by Berzelius, which says that organic compounds could be produced only under the influence of some mysterious vital force in living organisms, and artificial synthesis of organic compounds cannot be possible in test tube. And in 1828, one of his student, Berzelius' student, he observed a unique experiment. Through unique experiment, he observed that ammonium cyanate could be converted into urea, and this ended the vital force theory. These are the pictures of the two scientists, Jacob Berzelius on your left and his student Wöhler on your right. Now, why synthesis? Synthesis term was used first time by Kolbe. Basically, it means assembling of a compound, a chemical compound with various elements. So, for example, synthesis of acetic acid, synthesis of aniline, and so on. Now, the importance of synthesis can be several fold. Firstly, new compounds can be prepared which are not available from natural sources, and there may be some new compounds which are required by the society, for example, drugs, perfumes, and so on. Similarly, second important role of organic synthesis is in the proof of structure. For example, when structure of benzene was not proved, in those days, several structures, as you can see in this box, several structures were proposed for benzene, which had molecular formula C6H6. However, based on the synthesis, the structure of Kekule was accepted and all other structures were ruled out. Another important thing why organic synthesis is closely associated with organic chemistry is because the natural products that were isolated were all complex mixtures and they were often having closely related structures. And the isolation of a pure compound from these closely related mixtures was often very difficult. And even after this, the compound obtained in hand was generally just few milligrams. So this was basically a conversion of kilogram to milligram, kilograms of plant material to milligram of the product. On the other hand, it was seen that artificial synthesis usually gives readily separable compounds or products and they are available in reasonably good quantity. And because of these reasons, organic synthesis became intimately bonded with the mainstream of organic chemistry. And therefore, chemists tried to systematize this area of organic chemistry. Now, early design of synthetic routes was mainly an intuitive operation. Intuitive means there was no thought process involved. Just people thought that I could make this compound from this compound and they were trying to make it and reported it. And only notable exception was Sir Robert Robinson's synthesis of tropinone, which he reported in 1917. What he did is, this is the structure of tropinone. What he did is, he subjected this molecule of tropinone to imaginary hydrolysis at these 2 points, which are circled here. And he thought that if I carry out hydrolysis at these 2 points, what products would I get? And then he thought that he would get succinyldialdehyde, methylamine, and acetone by breaking this at these points. And therefore, then he thought that if I mix all these 3 compounds, can I get tropinone? And indeed, he could get tropinone, although in low yield. And perhaps this was the first example of a target molecule being transformed into synthetic precursors, its starting materials, by a thoughtful strategy. And this is the picture of Sir Robert Robinson, who received Nobel Prize in 1947. Now, during last quarter of 19th century, that is 1875 to 1925, carbon chemistry was mainly based on availability of many aromatic compounds from industrial coal tar. The industrial coal tar was mostly available and therefore most of the starting materials were selected from this source, and therefore there was very little planning required because most closely related hydrocarbon, aromatic hydrocarbon that was available, that was taken as starting material and it was converted into useful organic compounds. And these include some of the compounds as shown on your screen like alpha terpinol, camphor, and so on. These are some aromatic compounds, aroma compounds. And the next century, quarter century, the synthesis became little more complex and complex molecules like this were prepared, such as quinine, which was found to be useful, having antimalarial property. And this was synthesized and reported by Sir R.B. Woodward, who received Nobel Prize in 1965. And he reported this synthesis in 1945. Then the next period of 1945 to 1960 witnessed little more complex compounds like this, where you have a control of stereochemistry at the double bonds, control of stereochemistry at these several stereo centers, as you can see this aroma compound set role. And the synthesis of more and more complex compounds was carried out and reported. However, as this period can be considered as a golden period because a lot of complex molecules were reported during this period, but still during this period throughout, each synthetic problem was approached as a special case, and much of the thought was unguided. That means there was very little planning involved, and therefore some principles of synthetic design were laid down. Now, what are the principles of synthetic design? Before that, let us first try to understand that to outline the principles of this synthetic design, that is how to synthesize a molecule, it's a complex problem because it involves a mental process, it involves direction of thinking and imagination, which may vary from one individual to another. And for making an organic compound or the synthesis of planning of organic compound, one must have these certain prerequisites, that is certain basic requirements that one should possess. What are those things? The knowledge of organic reactions. For example, we must have knowledge of aldol, Wittig, Michael and such other reactions and their mechanistic implications. Secondly, we must have knowledge of functional group transformation. Most of the functional groups are transformed or transformable into each other and this is very much required sometimes in the synthetic steps to adjust the oxidation state of the molecules. But one must remember that most of the functional groups are interconvertible by several reactions, and therefore if a functional group is present at a particular position in the molecule, you can easily transform it into another required functional group. So this is also a very important requirement. Then one must have familiarity with spectroscopic techniques. For example, one must have knowledge of infrared spectroscopy, UV spectroscopy, mass, NMR, and so on to prove the structure of the synthesized molecule. Similarly, one must have appreciation or knowledge of readily available starting materials. One must know what are the readily available starting materials to start with. Now, retrosynthetic analysis. Basically, what is this? It is basically reverse of synthesis. Like we do the synthesis in the laboratory, and here the synthesis is done on paper, the planning is performed on paper or executed on paper, and then it is performed in the laboratory. So it is basically reverse of synthesis, in which a target molecule which we want to synthesize is dissected at suitable points, which leads to some simpler compounds in the reverse direction. Now, what are simple compounds? The compounds may be synthesized in 4 or less synthetic steps from inexpensive commercial compounds. Professor E.J. Corey in 1964 discussed for the first time the idea of designing organic synthesis, and he demonstrated a very beautiful synthesis of longipholin with an example. What he did is, this is the structure of longipholin, and he thought that if we break the bond between carbon number 1 and carbon number 2, we get its skeleton like this. So basically what he did first, that he detached the appendages, that is this methylene methyl groups, and then he focused on only the construction of the carbon skeleton. And there he thought that if I break a bond between carbon 1 and 2, I can get a skeleton simplified like this, right? And then if you unfold this is actually a folded form. If you unfold it, you will find that there is a 6-membered ring and another 7-membered ring. Both are fused with each other. And carbon number 1 and carbon number 2 are positioned like this. Now, if you make such a compound and if you can connect carbon number 1 with carbon number 2, you may get the longipholin skeleton. And this was his simple idea. And he further thought that if I have this skeleton, which is nothing but a homodecalin skeleton, 1 carbon more than that of a decalin system, I can make this type of homodecalin skeleton from decalin by addition of 1 carbon unit. So this way, he presented his idea of synthesis of longipholin, and he demonstrated the planning of organic synthesis for the first time. So let us see what is his definition of retrosynthetic analysis. He said that retrosynthetic or antithetic analysis is a problem-solving technique for transforming the structure of synthetic target molecule into a sequence of progressively simpler structures along a pathway which ultimately leads to simple or commercially available starting materials for chemical synthesis. So basically, he has said that you can transform any complex molecule into simpler structures by breaking certain bonds at some suitable points and convert them into simpler compounds. And these simpler compounds can be still converted into still more simpler compounds by breaking suitable bonds. And this process can go on till you get simple compounds. And in this process, the transformation of a molecule to a synthetic precursor can be accomplished by application of a transform. There is something called transform, a very useful term, which is indicated by a double line arrow. This is denoting exact reverse of synthetic reaction to a target structure. So when we go in the laboratory, in the forward direction, you can convert X into Y. But here, if you want Y, Y can be obtained from X, and then Y to X transformation can or conversion can be indicated by this transform. This is the symbol of transform. Basically, transform indicates a reverse of synthetic reaction. And each dissection corresponds to a chemical reaction. Whatever bonds you break, it has some chemical significance. You must be able to make that bond in the chemical reaction or synthetic sequence. So this is the picture of Sir E.J. Corey, Professor E.J. Corey, and this is the book in his hand he is holding, which is having title Logic of Chemical Synthesis. Now he further defined, or he gave some concepts of synthons and synthon equivalent. What are synthons? According to him, they are defined as the structural units which become idealized fragments as a result of disconnection of CC bond or CX bond, X stands for heteroatom, in a retrosynthetic step or a transform. So basically, when you break a bond, CC bond or a CX bond, you are getting some fragments or some pieces of the molecule, and these pieces are called synthons. Now what happens that many times when you break a bond, you are getting positive and negative charges, and they are not stable compounds, and therefore you need some chemically stable neutral equivalent reagent, and those compounds are called synthon equivalents. So he defines synthon equivalents as neutral chemical compounds corresponding to synthon. So the whole process is shown here, represented here by a simple flowsheet diagram like this. A target molecule can be converted into its intermediate by application of a transform. Intermediate 1 can be further simplified into intermediate 2 by application of a transform by breaking certain bonds at suitable points, and this way you can reach to starting materials. Let us take an example to understand this process. For example, if you consider the synthesis of 2-carboethoxycyclopentanone, right? If you want to make this molecule, what you can do is, if you consider breaking a bond at this position which I have shown here, right? Then this is the transform, and this is the route A. If you break a bond between this carbon and this carbon, you are getting synthons like this, right? Now synthons, as I have told you, they may have positive or negative charges. Let us try to put positive charge here and negative charge here, right? And this is, as we know, that this is the correct polarity. Similarly, you can also have negative charge on this carbon and positive charge on this carbon in another option, that is B, right? However, option A is correct because it shows the positive charge on carbonyl carbon, right? And this is the natural polarity of carbonyl carbon. And therefore, when you break a bond like this, and when you are pressing the charges like this is the correct polarity, and this is a suitable synthon. And therefore, if we consider further that how do we create a positive charge on this carbon, then you can consider some leaving group like alkoxy or some other group which can create a positive charge on this center. Similarly, how do you create a negative charge? If a proton from this position can be abstracted by a base, this is an acidic proton, and therefore if it is abstracted by action of a base, you can create a negative charge. And therefore, to consider or to appear or to reach to this neutral synthon, you need to simply place a proton, but you don't show it. And therefore, your new target or your new starting material can be defined like this, right? And this way, you can carry out the synthesis. Actually, it has been reported, Dickman cyclization, that this particular compound can be obtained via the same compound by application of a base along this pathway. So this example demonstrates how to break a bond, how to put charges, and then how to carry out the synthetic sequence. Now, you may think that why disconnection at this particular position only? You may have a disconnection at this position or breaking a bond at this position or this position. Very well, it is possible. However, if we see that if you break this bond, then you may put positive charge here, negative charge here, right? And these are not good synthons because they are not going to give you very easily simple starting materials. If you break a bond here, then you may end up with positive charge here and a negative charge here. Now, as you can see here that you have some 2 electron withdrawing groups here, and negative charge will be stabilized here. And therefore, you may have this as a good synthon. But if you consider its probable starting material, you may not end up with a good or easily available commercial starting material. And therefore, this also is not a feasible breaking. Now, question is how to disconnect and where to disconnect. So the answer is very simple, that first of all, whenever you have a target molecule to be disconnected, you must look for first carbonyl group in its various forms. For example, carbonyl group may be present in the form of aldehyde, ketone, ester, and so on. Then you have to look for double bonds, conjugated or isolated. And then finally, you have to look for other groups like nitro, hydroxy, amino, cyano, etc. Now, there are some good guidelines. How to carry out disconnection? Some guidelines have been prepared, and those, let us try to discuss those guidelines. Now, what are those guidelines? First one is make synthesis as short as possible. So first thing is always try to make a shortest possible route to the target molecule, right? If you want to go from one place to another, you will always prefer a shortest route, right? You will not like to go by a longer route. Same way here, if the synthesis goes for commercial production, then that synthesis should carry minimum amount of investment, and therefore always it is preferred to have a shortest possible route, and therefore always consider minimum number of steps. Second important thing is use only disconnections corresponding to known and reliable reactions, right? You must always think of breaking a bond and thinking of making that bond using some chemical reactions which are known and reliable. That means only use reactions that you have seen that are existing, right? Do not invest chemistry, do not invent chemistry at this stage, right? You are not supposed to think of some new reactions that might give this kind of products, right? This is also one important tip. Then select disconnection corresponding to highest yielding reactions. There may be several possible routes, there may be several possible reactions, but out of those you have to think of highest yielding reaction. Then disconnect CC bond or CX bond if they are present, and if possible disconnect at a branch point. Whenever you see a branch, right, going or being developed in a molecule at some point, you can try to disconnect that branch, and then you can try to connect it in a synthetic step. Another important thing is disconnect rings from chains. If you have a side chain and if you have a ring, then always it is useful to attach the chain by some useful reaction, and therefore disconnection of rings and side chains is also an important aspect. Similarly, if the molecule is symmetric, then try to disconnect the molecule in the middle. As you can see here in the example of trans beta carotene, if you break the molecule at this point, you are going to get two similar fragments, right? And sometimes it is very easy to make them react to get the target molecule. And therefore, if possible, if you have a symmetric molecule, try to break the molecule in the middle. Now, if the target molecule is aromatic or heteroaromatic, then disconnect the bond between ring and substituents as we have discussed previously. For example, if you have a aromatic ring like this and if you have another ring attached to it, then the preferred points of disconnections are like this, right? And as you can see here, that we can make this compound from benzene and this acid chloride by Friedel-Crafts reaction. In case of polyfunctional compounds, the order of introduction of various groups is very crucial because all the substituents that are present already in the aromatic ring, they have directive effects, and therefore it is very important in what order you are introducing the groups into the ring. Let us try to see this with the example. For example, if you want to make, say, metachloroethyl benzene, right? Now, this is the metachloroethyl benzene, and if you try to make it from, say, chlorobenzene by ethylation, you will end up with ortho and para products, right? Similarly, if you try to carry out chlorination of ethyl benzene, then also you will end up with ortho and para products because ethyl group is also ortho para director. And therefore, you have to think of some group which is meta directing and still convertible into ethyl group at a later stage. And therefore, it can be carried out by using this route. For example, benzene converted into acetophenone and then chlorination and then reduction of this keto group to this ethyl side chain. This can be achieved. So this is also a very important tip, that order of introduction of groups is very important because they have directive influence. Then you have these pericyclic disconnections. Now, whenever you have a ring like this, and then you can carry out disconnection corresponding to pericyclic reaction, then you may end up with such type of synthons. Now, remember that these synthons, if you go along this movement of arrows, then you may end up with these two synthons. And as you can notice that there are no positive and negative charges. So these are pericyclic synthons. They are neutral. And therefore, you don't have to look for any suitable chemical reagent because these compounds themselves, these synthons themselves are neutral chemical reagent or synthon equivalent. Similarly, suppose you want to synthesize this molecule, right? And then if you break this molecule from this point, let us say this benzene ring and oxygen bond, if you are breaking, then you might end up with this O minus alkoxide and a destabilized benzene ring. And therefore, this reaction is not a favorable reaction because it involves nucleophilic attack of an alcohol on inactivated aromatic ring. However, if you try to break the bond between this carbon and this oxygen, then you have a phenoxide, right? This is a possible phenol is a starting material. Similarly, you can have some positive charge on acetic acid molecule, acetic CH2 plus COH like this, and therefore it is possible to connect these two by a well-known ether synthesis, and therefore it is preferred to have a disconnection at this point rather than this point. Now, functional group equivalence. Almost all functional groups can be converted into each other. Interconversion is possible. And therefore, there is something called functional group equivalence principle. So, principle of functional group equivalence states that almost all functional groups can be converted into each other. And this is the chart which I have taken from Jerry March. And this is a very useful chart. You must remember that these kind of functional groups can be converted into each other by several reagents, by several reactions as shown in this table. And therefore, this is also a very important principle that you must remember in mind, that if a position, practically if a functional group is present at a particular position, you can convert that functional group into any other functional group that you desire. And therefore, this is also, this knowledge or transformation of groups is also very, very important. Now, this kind of retrosynthetic analysis can have different types. There can be one group disconnection, two group disconnection, and so on. So let us try to see one group disconnection. Whenever you have one functional group in the molecule, then the target molecule, the bond cleaved is between alpha carbon and X, right? So for example, if you have this, if you say this is the compound, this is an ester, benzyl ester, a benzyl benzoate, and if you carry out this CO disconnection, then you may get the positive charge here, negative charge here, and that positive charge you can put some L as a leaving group, which can be chloride, and therefore this can be benzoyl chloride, right? And O minus stands for OH, and this is benzyl alcohol. So you can get these two starting materials for making this ester. Now, if the functional group has a carbon species instead of heteroatom, if you have a carbon species, for example, this ethyne, cyano, ester, etc., then the preferred bond cleaved is alpha carbon and functional group. So the functional group is attached here. The next carbon is alpha carbon, and it is possible to break the bond between alpha carbon and functional group. When the target molecule has two functional groups, then you can have it termed as two group disconnections. For example, now further, the relationship between two functional groups can be 1, 2, 1, 3, 1, 4, 1, 5, etc. with respect to each other, right? And both these functional group should be involved in the disconnection. Let us try to consider this case of 1,3-dicarbonyl system. This is a 1,3-dicarbonyl system. Now, if R and R dash are both same, right, then there is only one disconnection possible. You can break it from this side, right? As it is shown here, you can break it from this end, and you get what? One positive charge here on this carbon along the route A, right? If you break it from here, you get this positive charge on this carbon and a negative charge on this carbon, right? Similarly, if you break it from this side, then you will get positive charge on this carbon and negative charge on this carbon. And then synthon equivalent for both the cationic synthons is corresponding ester. So if this cationic synthon is considered, if you put OR here, then the corresponding neutral chemical compound can be obtained. Now, another important thing is that a bond between two functional groups is generally disconnected if you have this kind of functional groups, right? Any bond between these two functional groups is preferred, right? That will be the most suitable point. If you prefer to disconnect it at here or here, you may not get a good disconnection. But a bond between these two functional groups will be always useful disconnection. And this example we have already seen. Similarly, if you have 1,2 dions, then it is always preferred to have a disconnection at this point. Now, if you disconnect at this point, you may have this carbonyl carbon as positive and this carbonyl carbon as negative, right? And you may wonder that positively charged carbonyl carbon is possible. You can have ester and acid chloride and so on. But what about the negative charge? Now remember here that if you put positive charge here, you must place negative charge here. Otherwise, you cannot make the bond. And therefore, when you place the bond negative charge on this carbon, then it is natural polarity of carbonyl carbon is positive, and you are placing a negative charge. So this is the wrong polarity actually. And therefore, a use of Ampolung method is done, which we will see later on. And this can be possible. And therefore, you can achieve this kind of negative charge on the carbonyl carbon. Right. Then, let us try to see this principle of reactivity Umpolung. Basically, the term Umpolung means reversal of polarity. And if you see the normal polarity of carbonyl carbon, then we know that it is positively charged carbon and negatively charged oxygen. If this carbonyl carbon is conjugated, then you will see that the positive center is shifted to some other carbon due to this resonance, right? The negative charge is on oxygen. However, positive charge is no longer on this carbon, but it is present on this carbon, alpha beta carbon. Now, let us try to understand the process of this reactivity Umpolung with the example of heteroatom S. As we have seen in the previous case, sulfur atom is used and it can be converted into 1,3-diethyne like this, and there you can have thioketal formed. Thioketals can be obtained from corresponding carbonyl system, and these thioketals now have this hydrogen which couldn't be alkylated otherwise. Now it is acidic hydrogen, and therefore on treatment with a base like normal beta lithium, you can abstract this proton and create this negative charge. Now you can see that carbonyl carbon earlier was positively charged, but now here the same carbon is now negatively charged. And now alkylation is possible. You can carry out alkylation with alkyl halide, and then removal of this sulfur functionality can be achieved using this reagent to get the ketone. So this way you can achieve the reactivity umpolung or reversal of polarity on the carbon which is positively charged, and you can convert it into negatively charged carbon. This umpolung method can be very useful and it can be applied in many interesting applications. For example, benzaldehyde can be converted into this particular ketone. Now generally aldehyde to ketone transformation is not very easy, but via the formation of these dithions you can achieve it and you can alkylate at this position. Now here is an interesting example that formaldehyde, it has now two hydrogens, right? And therefore if you create some kind of diethyne like this from formaldehyde, then both hydrogens are acidic and both of them can be alkylated with this kind of dihalide to create a cyclic ketone like this. So these are some of the useful applications of umpolung method. Now, like sulfur atom we have seen in the previous case, magnesium and phosphorus also can be useful in bringing about this reversal of polarity. When you use magnesium, we always know that Grignard reagent is well-known example, and you can have magnesium on reaction with alkyl halide to give corresponding Grignard reagent. Now, if you see that normal alkyl halide has positive charge on carbon, but when it is Grignard reagent, then the same carbon now becomes negatively charged because now it is connected to magnesium, electropositive, right? And therefore you can see that the polarity is reversed from positive to negative on the same carbon. As we know that Grignard reagent is having this equilibrium and it is stabilized by this solvent pairs to this Schlenk equilibrium. So this is an application of Grignard reaction, that cyclohexyl chloride converted into cyclohexyl magnesium chloride, then it is treated with acetone and consequently it is converted into this cyclohexenyl isopropenyl cyclohexane, right? Similarly, when you consider using phosphorus as heteroatom, if phosphorus triphenyl phosphine is treated with alkyl bromide, then you can get corresponding phosphonium bromide and then it can give you corresponding triphenyl phosphorane, and then this is the famous Wittig reaction which gives ultimately triphenyl phosphine oxide and isopropenyl cyclohexane. Same product like this, right, from the different starting materials. So this way you can have the reactivity umpolung. In this case again, as you can see here, that the carbon which is earlier positively charged, now it is negatively charged. Here also isopropyl bromide, the carbon is positively charged here connected to bromine, which is now same carbon. In this particular case, it is negatively charged, right? As you can see here. So this way you can create a negative center on the positive carbon. Now there is another important concept of convergent and linear synthesis, convergent or parallel synthesis. Now, what is the difference? When you carry out synthesis of big molecules by step-by-step fashion, stepwise fashion, you go on adding one element or one component one by after the other, then you can achieve this linear synthesis to create a bigger molecule, right? As you can see here that if you start from this AB, then A, B, C, you go on adding C, then you go on adding D, then E, and so on. You get this A, B, C, D, F. On the other hand, other approach is to add small chunks together. Like you first make A plus B, right? At the same time, you have C plus D to make CD and E plus F components to make EF. Then you can attach these CD and EF components to make CD, EF component. Similarly, then you have this AB component ready, and then you can attach this component to this bigger component to achieve the synthesis. And this way, the synthesis is carried out in parallel, and therefore this is called convergent or parallel synthesis. This is the stepwise fashion, and therefore it is called linear synthesis. Let us see what are the uses of these two syntheses. If you consider a 7-step sequence of say A to H and assume that 90% yield is obtained in each step. Normally it is very difficult to achieve 90% yield, but let us try to assume 90% yield. And further, it is very, very rare to get 90% yield of all the steps. But still, let us try to assume this ideal situation. Right? Let us see what is the overall yield. Now, there is something called overall yield. What is overall yield? Overall yield is the product of percentage yield of each step multiplied by 100. So assume that the first step gives A to B in 90%. Similarly, B to C transformation is also 90%. This goes on and on. And finally, we get H. Now, what is the overall yield of this process from A to H? It is found to be 47% by this formula, right? And 47% is the overall yield. Now, if you consider a parallel synthesis means you start with two starting materials at a time, convert them into the respective first step products. By here also let us try to assume that all the steps give you 90% yield, right? Now 7-step sequence here also we are considering a parallel synthesis, but 7 steps. For example, 1 2 3 4 5 6 and 7. So 7-step synthesis is here also. And if you consider here also again 90% yield of each step, then you will find that there is overall yield of 59% in this overall process or a parallel process. And parallel process means you start with 2 starting materials at a time, 3 starting materials at a time, and carry out reactions in parallel, right? So these reactions can be carried out independently, simultaneously, on the same day during same time, because they are two different reactions. You can carry out these reactions into independent vessels, and therefore it is possible to have this kind of reactions carried out in parallel. So the advantage is that when you carry out a 7-step sequence with 90% yield of each step, then your overall yield is 47%. However, if parallel sequence is considered, your overall step for same number of steps with same percentage yield of each step, you are getting 59% of overall yield. That means this is always a better process because you are getting a better overall yield of the final product. So if you have a 3-step sequence, assume that 90% yield is given in each step or obtained in each step, then a 3-step sequence overall yield is obtained 73%. If you have a 5-step sequence, overall yield is 59%. If you have 7-step sequence, overall yield is 47%. Now parallel synthesis can also be carried out in this way also, that you can have 4 chunks prepared simultaneously in the parallel fashion, like A plus B gives D, AB. Similarly, C plus D simultaneously can be carried out to give CD, then E plus F gives EF, and G plus H gives GH, right? And then these chunks can be further connected to each other, and then it can be converted into this. Again, you will see that this is a 7-step sequence, but overall yield is now 73%, right? So then this way you can see that convergent sequence or convergent synthesis, parallel synthesis is always preferred or always better if you have long steps or too many steps in the reaction sequence. Now let us try to consider the merits of the two processes. In linear synthesis, as we go from A to H, from the starting material to the last product, each of the intermediate product becomes increasingly precious. It becomes increasingly precious. That means you have carried out some reaction, you have prepared the first stage product, you are doing some more reactions, then you are preparing second stage product, third step product, and so forth. So each of these product is having investment of your time, money, efforts, and so on. And therefore, each of the product as you go ahead in the linear synthesis becomes more and more precious, increasingly precious. And therefore, the loss of any product at an advanced stage is a catastrophe. It can be a disastrous. Any loss of this product, let us say in this step, say G step, right? If it is lost then after a 7-step sequence, right? Then it can be a catastrophe. It can be a disaster, right? On the other hand, in the convergence, further one more thing is, in the convergent synthesis, the loss of a product in the advanced stage may not be that big loss. Now, same thing that if you have this parallel synthesis, then any product lost in the advanced stage can be very easily, quickly prepared, right? And therefore, this may not be a that big loss as considered in the linear synthesis, right? And therefore one must remember that the linear synthesis has this drawback that advanced product becomes increasingly precious and any loss can be a catastrophe. So the message is that the short synthesis we should use linear approach, for long synthesis we should use convergent approach. Now, considering one important aspect, that is remote functionalization, right? Now, this synthesis is carried out with several concepts like control, selectivity, and so on, right? So there is called bridging. This is called bridging regio control. Bridging regio control means there is a control element operating when you have a reaction to be carried out at a one particular specific site, and bridging term is used to indicate that the molecule, the body of the molecule itself acts as a bridge or the reaction center, right? That can be understood if you consider this reaction, this process. So for example, if you have this molecule and if you have a hydroxy center at this stage, this steroid molecule, it's a big skeleton, big molecule, and if you have a alcoholic unit here, OH group here, and if you treat it with NaCl, nitrosyl chloride, you get corresponding nitrite ester, and this nitrite ester on photolysis gives you corresponding oximes. Now you can see that this hydroxyl group is present at this position, and if you see, look at the products, then the products have the hydroxyl group at this position again, but now you have oxime functionality obtained at this particular position, right? This is the shoulder methyl group, and you have this oxime functionality obtained at this position. Similarly, another oxime functionality in another product is obtained at this position, right? So two isomeric oximes are obtained by photolysis of this nitrite ester. Now, this was an interesting experiment that was demonstrated by this Ronald Breslow, this another great scientist, a versatile physical organic chemist, right? He introduced, or he studied this reaction, and he proposed this mechanism. See, what happens is if you have this hydroxyl group at this position, 11 position, and when you carry out this fragmentation or this photolysis of nitrite ester, then you will get this oxygen radical and nitrile radical dissociates. Now, once this oxygen radical is obtained, then this oxygen radical can abstract a hydrogen from this neighboring axial methyl group, and therefore this oxygen radical will become OH group and a new radical is formed here. Now what happens is if this new radical formed here abstracts this nitrosyl radical which has got dissociated earlier, if it recombines, then you will get this nitroso functionality at this position, and this nitroso functionality is nothing but it is a tautomer of this oxime. So you can get an oxime at this position. This was beautifully explained by this scientist, and he showed that he demonstrated that the body of the functional group, body of the molecule, and the orientation of these sites, reaction sites itself acts as a bridge, and therefore the reactions are possible across this bridge, and some reactions at unactivated centers can be achieved. Now there is another regio control called protective regio control. What happens is if you have a molecule like this, then if you try to convert it into its ketal, then what happens? That ketalization takes place at this position. Now you see that there are two carbonyl groups, but ketalization takes place at only this carbonyl group. This is a conjugated carbonyl group, this is unconjugated carbonyl group. And therefore, it is found that the ketalization takes place at the unconjugated carbonyl group. The reason being, the conjugated carbonyl group has this positive center created or displaced at some other carbon, and therefore the reaction of ketalization does not take place here. This protective regio control is demonstrated like this. Similarly, a beautiful example was explained or demonstrated by another scientist called Professor Z. Valenta. Now here he took advantage of adding Lewis acid and creating or changing the electronic environment in the molecule. What he did is, let us try to understand this with an example. He wanted to have this product. Now this is the desired product, and this is a quinone moiety. Out of attached to it is another cyclohexene unit here, right? And as we can easily think that this particular compound can be obtained from the corresponding diene unit here and a quinone unit like this, right? And this is a very easy, simple reaction, and it should give you, by a 4+2 cycloaddition, it should give you this, right? Now actually what happens, that when he tried to react these two components, then he found that the desired compound was minor and this was obtained as a major product, right? What is the difference between major and minor product? He wanted to have this compound in which the two methyl groups of this quinone moiety and this methyl group, they are on the opposite side. And here in the major product, the methyl group and the two methyl groups of the benzoquinone moiety, they are on the same side, right? So, or they are close to each other. So this was the minor product obtained, which was desired, and this was the major product which was not desired. Then what he did is, he thought of carrying out the reaction using Lewis acid. See what dramatic change he observed, that when addition of BF3 takes place, then the whole course of the reaction is found to be different, and he got the minor product which was desired in the major quantity. And he offered explanation like this, that the lone pair of oxygen coordinates with this Lewis acid to form this kind of anion, oxygen anion, and then this is a resonance stabilized system in which you have a positive charge now created at this carbon and this carbon, right? And both are equivalent, and therefore you have a positive center at this or this carbon. This is one thing. Then he also offered another important explanation, that this cyclopentadiene is 1,3-cyclopentadiene has this methyl group which has electron releasing nature, and therefore this releases electron, and then through this kind of delocalization, this delta minus charge, or through inductive effect, delta minus charge is created on this carbon. Now you can see that delta minus charge is created on this terminal, positive charge is created on this terminal, and therefore the reaction takes place in the direction of a desired product, and he got this product. So this is how you can change the course of the reaction by simply changing the electronic environment by addition of Lewis acids. Now this is another example which is taken from a book which has, suppose you have this alcohol to be prepared, right? Then the easiest way to prepare alcohol is by removing this leaving group, this pair migrates here and you get this starting material, right? So basically you can prepare this alcohol by reaction between this X minus and a ketone like this. And this is the example. Suppose you want to prepare this particular alcohol, tertiary alcohol, in which you have this ethynyl unit, methyl and phenyl, three groups are there, right? Then this ethynyl unit can go, and this is a stable because acetylides are acidic, and this proton which is acidic can be lost to base, and you can have a carbanion like this, and this carbanion can attack on this ketone, and you get this particular tertiary alcohol as demonstrated in this example. Similarly, let us try to see the case of tertiary alcohol. If you have a tertiary alcohol in which all the three groups are different, methyl, phenyl and ethyl, then either you can remove this ethyl group to end up with this particular synthon, and this ethyl minus can be ethyl magnesium bromide, and react this ketone and this ethyl magnesium bromide to make the tertiary alcohol. Similarly, you can make this methyl go, so therefore methyl magnesium bromide can be used to react on this ketone with ethyl group here and to get the same tertiary alcohol. Similarly, you can carry out the reaction with phenyl magnesium bromide with methyl ethyl ketone to get the same tertiary alcohol. So this way you can have a lot of options and you can select one of the best options. Now whenever you have two identical groups on this tertiary alcohol unit, then the best disconnection is to begin with the ester group having third group, that is cyclohexyl, and then react with two equivalent of Grignard reagent. For example, if you have the two same groups like this, two methyl groups here and a cyclohexyl group here, and if you have this type of tertiary alcohol, then you can carry out the reaction of two mole equivalent of methyl magnesium bromide on this ester. Now this ester, as you can see here, cyclohexyl group is already present, and then you can get the tertiary alcohol. The same reaction can also be carried out by using this cyclohexyl magnesium bromide with acetone, right? And then also you can get this kind of tertiary alcohol. Now let us try to consider the synthesis of this violent measure ketone, which we have seen earlier also as an example of protective regio control. So suppose you want to make this violent measure ketone, then as first of all, whenever you have a target molecule like this, first thing you should observe is, as I have told you, that look for carbonyl groups in its various forms. So as you can see here, we have a carbonyl group here, we have a carbonyl group here. This carbonyl group is conjugated, this carbonyl group is unconjugated, and you have this ring junction methyl group also here. So this particular alpha beta unsaturated enone can be obtained from corresponding aldol. That we know aldol reaction is very well, and therefore we can have this aldol coming from this kind of 1,5 dicarbonyl system. 1, 2, 3, 4, 5. So 1,5 dicarbonyl system gives you corresponding cyclohexenones that we all know, right? So this breaking is done by this bond is broken, and you can have a negative charge here, right? And then this carbon ion can attack on this, and you can get this aldol. So this is how the reaction transform is applied. Now, to transform or to convert this into still simple starting material, another bond to be broken is here, right? So as you can see here, if the bond is broken here at this point, then you have a negative charge here, positive charge here on this fragment, right? Now negative charge here is quite feasible because you have got two ketonic groups here sandwiched outside, and therefore it is very easy to create a negative charge here. And this can be created by simply removing a proton from this substrate, right? So this is synthon and this is synthon equivalent. Now what about this synthon? This has a positive charge here, and this can be easily considered that this is an equivalent of this methyl vinyl ketone, right? As we know that methyl vinyl ketone, if you consider like this, it has a positive charge at this beta carbon, right? And therefore you can carry out the synthesis of this particular compound via this kind of starting materials. Now consider the case of this ketal, right? As you can very easily identify, these are the two, this is the ketal functionality, and very easily one can come out with this kind of possible static materials, acetone on this side and a diol of this type. So reaction of this diol with this ketone under acidic conditions will give us ketal, right? So breaking at this point and this point simultaneously with this functional group equivalence, functional group interconversion, you can have this ketal obtained from this, right? Now this butene diol can be obtained from corresponding ethyne and formaldehyde units, right? 2 moles of formaldehyde and then ethyne, right? These are acidic hydrogens, and they can be abstracted by action of base, and they can attack on this carbonyl functionality here, and this removal of proton from this side can attack on this carbonyl, and you can get this butane diol. So this synthesis also reported and carried out along this strategy as we have discussed. Now consider the cage compound as mentioned in this slide, right? Now making this kind of cage compounds, at a glance it looks very difficult that how to make this complex compound. But if you just try to apply this technique of retrosynthetic analysis, if you see that these blue bonds are there, right? So it is possible to break these 2 blue bonds, right? When you break 2 blue bonds, what do we get? We get a substrate like this. That these 2 double bonds are there, and a photochemical 2+2 cycloaddition can be carried out, and this can give rise to this formation of cyclobutane ring, right? And this is nothing but this type of tricyclopentanoid moiety. But this is not a very easily available system, right? Therefore, think of breaking some other pair of bonds. Now if you break red bonds, right, so red bonds are shown here, and if you break the red bonds, what are you likely to get? You will be getting a double bond here and double bond here at this position. So you will get basically an immune system like this, which is very easily understandable, or very easily you can imagine that this type of system can be obtained by cycloaddition of cyclopentadiene and benzoquinone, right? This is simply cycloaddition product of cyclopentadiene and benzoquinone, right? So therefore, a very simple way of making this cage compound will be via thermal thermal cycloaddition of this, and then photochemical cycloaddition of the resultant adduct. That is also achieved and reported in the literature. Now let us consider the synthesis of this molecule. Now this is an iterative sequence. Iterative means repetitive, right? You have two cyclobutane rings as you can see here, and the last terminal cyclobutane ring has two carboethoxy groups or two carboethoxy moieties. Now if you break this two bonds simultaneously, what you are likely to get? You will get this diethyl malonate, right? Because you have this carbon which is connected to two electronegative groups, and therefore this is acidic methylene, and you can have this diethyl malonate as its synthon equivalent. On the other side, this has a minus charge, so therefore these two carbons will have a positive charge, and that can be compensated by putting a bromine atom on each of the carbons, and therefore now you have a bromine as a good leaving group. It will go and create a positive charge here, right? So the dibromide is another synthon equivalent, diethyl malonate is another synthon equivalent. The reaction of these two will give you this, right? And the reagent required will be base. Of course, the base will abstract a proton from here, and then the carbanion will attack here, bromine will go. Similarly, another bond will be formed at this position simultaneously. So you can make this system very easily from these two units, right? Now let us try to see how you make this. Diethyl malonate is a readily available starting material. But what about this dibromide? So it is not easily available. So it can be obtained from corresponding hydroxy compound, right? You can treat it with some brominating agent and convert it into dibromide. Now how do you get this diol? This diol can be obtained by reduction of a dicarboxylic acid like this, right? And this dicarboxylic acid can in turn be obtained from corresponding ester by hydrolysis, right? And effectively what you have got, basically you have got another diester unit on the cyclobutane ring, exactly like the first situation, right? So again you apply the same strategy, break these two bonds simultaneously, again you will get diethyl malonate, again you will get the corresponding dibromide, and you can achieve this cyclization to get this system, right? Now how do you get this dibromide? This can be again obtained from the corresponding ester, right? Because this dibromide can be obtained from corresponding alcohols like this, as I have shown you earlier. These alcohols can be obtained from the acids, and acids can be obtained from esters. So ultimately, this dibromide also can be obtained from the corresponding diester. Again, you can have this alkylation of the diethyl malonate, and you can attach these two R groups also in this way, in this manner. So this way, you can see that this iterative sequence makes use of continuously same order of reactions in the same way to create cyclobutane. So like this, you can have 1, 2, 3, 4, as many as you want, and you can go on creating this type of systems in this fashion. So this way, retrosynthetic analysis can be useful in making many interesting molecules. Now this is another example with 3 phenyl rings, a terphenyl system, right? In the terphenyl system, it was beautifully explained, or it was thought that the central aromatic ring can be obtained from the corresponding cyclohexadiene unit like this, in the first step, right? So the first transform is that this diene unit can be obtained from the diene unit can be converted into aromatic system like this, right? And this diene can be easily converted into aromatic system because there is a force, or the driving force is the aromatization, and therefore it was thought that it can be obtained from this diene unit. Now this diene unit, what is the advantage of converting this aromatic system into diene unit is because it is further simplified very easily, right? So this is simple 4+2 cycloaddition of dimethyl acetylene dicarboxylate and a diene system like this. This diene system also can be achieved by making a Wittig reaction of these two units. Two double bonds can be created via Wittig reaction, and you can make this diene system. So the synthesis was carried out like this, as shown here, that paracresol was used, then it was brominated at the benzylic position using bromine and light. Then it was then the Wittig reaction was carried out to create this diene unit. Then it was treated with dimethyl acetylene dicarboxylate. A 4+2 cycloaddition gave this corresponding diene that we have obtained in the first step as a transformation. And then this diene can be very easily oxidized to give the terphenyl system, because the central ring has a driving force. Driving force is the aromatization reaction, and just air also is sufficient to carry out this transformation. So this way you can carry out this complex terphenyl system also from a very simple molecule like paracresol. Now another important example is of twistane, right? The twistane molecule, as the word itself shows, that the bonds are twisted, or the molecule is twisted, and it has two bonds like this. One is in front and another is in back. So backside bond is 1,6 bond, and this is the front side bond. And this type of molecule also can be very easily synthesized if you apply principles of retrosynthetic analysis. So how it goes? Break 1,6 bond first, right? So if you break the 1,6 bond, then you can have a negative charge on one carbon and positive charge on another carbon. Now what if you can simply convert it into a Decalin system? It is basically nothing but a Decalin system, and it can be oriented, or it can be shown like this, right? The carbon number 1 and carbon number 6, they are shown with these tiny balls, right? So basically you have a negative charge on carbon number 1, positive charge on carbon number 6. How do you create this? You can have a leaving group on carbon number 6. So leaving group will go away, leaving a positive charge here. It will take away a pair of electrons from this bond, and therefore you will get a consequently positive charge here. And you can have a keto center here, so that you can have a negative charge on this carbon, because this methylene becomes acidic, right? So these are the two options. Either you can have a L here, and to create a negative center here, you can have a keto group here, or you can have a keto group here. In both cases, you will get negative charge here and positive charge here, right? And then treatment of a base with this kind of system will abstract a proton from here, then it will attack in the intramolecular fashion on this carbon, and leaving group will go, and consequently carbon number 1 and carbon number 6 will get connected to form this kind of twistane unit. So this is the whole strategy, and therefore it was thought that A can be obtained from this A dash, right, in which L is a leaving group can be OH, and this can be obtained from this ketone by simply reduction of this keto group, and this can be obtained from this kind of enone system like this, A triple dash. So the synthesis was carried out like this, as we know that last intermediate A triple dash is here, right? This can be assembled by a reaction of 1,3-cyclohexadione and methyl vinyl ketone using base with a Robinson annulation reaction, and this gives you the intermediate of this type, and this via a sequence of reactions Q, which is shown here, it can be transformed into this required alcohol and ketone unit oriented at this position. So what is that system or the reaction sequence? You treat it with ethylene glycol in the presence of acid, and the ketalization takes place at this center, as we have studied or we have seen in the protective regio control, right? This is conjugated enone system, and therefore you will not get ketalization at this position. The ketalization will take place here. This keto group will be protected, and only this keto group will be enone. Being enone, it will be exposed, right? And then you carry out reduction using hydrogen and catalyst, and then you will get the corresponding hydroxy ketone system, right? So this reduction will reduce the double bond also. This will reduce the alcohol group also, keto group to alcohol, and you will get this keto alcohol unit as required, right? Then it is methylated, right? Methane sulfonyl chloride is used, and methylation is carried out. This methylation is giving you a good leaving group, methylate, and therefore the reaction becomes facile. Now what happens? You have a carbon ion created at this position by the action of a base. The carbon ion created here will attack here on this center. Methylate will go and the bond will be formed. This was the bond that we discussed earlier, that carbon number 1 and carbon number 6. This bond is created here, crucial step, right? And then the reduction of the keto group using zinc and ammonia, zinc amalgam and HCl gives twistane. So this is how the complex molecule like twistane also can be assembled via a simple thoughtful strategy of retrosynthetic analysis. Now in the retrosynthetic analysis, what we should remember is that there may be more than one route to synthesize or prepare target molecule, but selection of the route is based on the following factors. You must always consider following factors in mind. The highest overall yield, whatever route gives you highest overall yield is the most preferred route. Then availability of starting materials is also to be considered. Which starting materials are easily available, commercially available, economical, and so on. Then cost of the starting materials, as I mentioned, is also very important. Cost of the reagent is also important. It may happen that you may have easy, commercially available, cheap starting materials, but reagent may be costly, and therefore you have to consider those economic aspects also. Then the route which involves least time and efforts. As I have told you, that shortest possible route has to be decided, and therefore you have to select that particular route which involves least time and least efforts. And the route which involves less number of separation steps, because separation is also a crucial factor during experimentation, and therefore this is also an important factor or aspect to be considered. Now here we have some important terms to be encountered in organic synthesis. Total synthesis. Total synthesis is the chemical synthesis of a molecule from a relatively simple starting point. So this is basically a complete synthesis starting from simple compounds up to the final target molecule. Then semi-synthesis. Semi-synthesis is a synthesis of a molecule from an advanced precursor related to it. So here you start with an advanced precursor and go to the final product, final target molecule. This is called semi-synthesis. Then you have another term called formal synthesis. It is a synthesis of key intermediate that has been already converted into a target molecule. So when the target molecule is already achieved via some route, and then you prepare some advanced intermediate of that, then it is called formal total synthesis of that particular target molecule. Then you also have partial synthesis. Partial synthesis means synthesis of a partial or a part of the molecule or a portion of the molecule. So these are some of the important terms that we encounter in organic synthesis. These are some important books. These are the books. One is called Organic Synthesis, the Disconnection Approach by Stuart Warren. And another is Designing Organic Synthesis, a programmed introduction to the synthon approach by Stuart Warren. And then the book which I have discussed in the presentation, E.J. Corey, The Logic of Chemical Synthesis. These are some important books that you can refer for understanding the concepts of this area further. Thank you.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.